What if I told you there's this one single formula that can, literally correct your gut feelings? A formula that helps you see the world more clearly. And get this, it even powers the AI that's all around us. Well, today we're diving right into that formula. It's called Bayes' theorem. All right, let's kick things off with a little puzzle. Imagine this. You're a programmer. There's this super rare security bug out there. It only exists in, say, 1% of all code. So you run a scanner on your work, and the scanner's really good. It's 99% accurate. And ding, it flags your code. So what's your first thought? Well, the scanner's 99% accurate, so it's gotta be a bug, right? I mean, what does your gut tell you right now? So if you're sitting there thinking, yeah, it's almost definitely a bug, you're not alone. That's what most people think. But you're probably wrong. This is a classic brain teaser known as the false positive paradox. And it's a perfect example of how our intuition can just completely lead us astray when we're dealing with probabilities. The real answer is, well, it's pretty surprising. And to figure it out, we're going to need a special tool. And that tool is, you guessed it, Bayes' theorem. See, most of the time, we think about probability in a forward direction. Like, if I have a fair coin, what are the odds I'll get heads? Simple enough. But Bayes' theorem flips that whole script. It's all about inverse probability. It asks the question backward. Okay, I've seen an effect. The coin landed heads up, or in our case, the scanner went off. Now it's the probability of a specific cause. So what is this thing really? Well, at its heart, Bayes' theorem is just a super logical way to update what you believe. It's a formula that lets you take an initial guess, we call this a prior belief, and then tweak it or adjust it based on new evidence you get. It's basically a mathematical recipe for learning from experience. There's this great quote that I think just nails it. It says, Bayes' theorem is the mathematical process of turning hindsight into insight. I love that. It means you can look back at what happened, at the evidence, and use it to get a much sharper, more accurate picture of what's really going on. It's a framework for learning from the past. Okay, so to actually use this thing, we gotta understand its four key parts. Let's break them down. First up is the prior, which we write as P of A. This is just your starting belief before you have any evidence. So in our little puzzle, that's the 1% chance that any random piece of code has a bug. Simple. Next is the likelihood, P of B given A. This one asks a specific question. If the code does have a bug, what's the probability the scanner will catch it? Well, that's our 99% accuracy rate. Then you have the evidence, P of B. This is just the overall chance of getting an alert, period, whether it's a real bug or a false alarm. And finally, the big one, the posterior, P of A given B. This is the answer we're looking for. It's our new, updated belief, the real probability of a bug after we've seen the alert. And here it is, the master formula itself. P of A given B equals P of B given A times P of A, all divided by P of B. Or, in plain English, our updated belief equals the likelihood times our initial belief divided by the total probability of the evidence. I know, it looks kind of simple, right? But trust me, this little equation is the key that unlocks not just our paradox, but a whole lot more. All right, enough theory. Let's put this formula to work and actually solve our little code scanner problem. We're going to walk through this step by step, and you'll see exactly how we get to that pretty wild conclusion. Okay, let's make this really concrete. Forget the percentages for a second, and just imagine we have, say, 10,000 chunks of code. Our prior belief is that 1% have a bug, right? So that means 100 of them are buggy, and the other 9,900 are perfectly clean. So far, so good? Now let's think about the alerts. Step 2, the real alerts. The scanner is 99% accurate, so it's going to correctly find 99 of those 100 real bugs. Great. But, and this is the part where everyone gets tripped up, step 3, the false alarms. What about those 9,900 clean pieces of code? Well, the scanner has a 1% error rate, which means it's going to incorrectly flag 1% of them. And what's 1% of 9,900? It's 99. So now look what we have. 99 real alerts, and 99 false alarms. So your scanner goes off. What is the actual probability that your code has a bug? Well, it's the number of real alerts divided by the total number of alerts. That's 99 real ones divided by the total of 99 real plus 99 false ones. So 99 divided by 198, which is exactly 1/2. 50%. 50. Not the 99% your gut was screaming at you, was it? And this is a perfect illustration of the formula in action. The probability of a bug, given an alert, is the rate of real alerts divided by the rate of all alerts combined. The logic leads you right here. So what's the big lesson here? It's this. When you are looking for something that is incredibly rare, and that initial 1% chance is what we call the base rate, even a super accurate test can be really, really misleading. Because the bug is so rare, you just have this huge ocean of clean code, and even a tiny error rate in that huge ocean creates a flood of false alarms, enough to completely match the number of real alarms. And this isn't just about code. This applies to everything from medical tests to security checks. Okay, so this is way more than just a cool brain teaser to stump your friends with. Bayes' theorem is an absolute workhorse. It is running quietly in the background of so much of the technology that we use every single day. I mean, think about your email spam filter. That's pure Bayes. It starts with a belief about whether an email is spam, and then it sees words like prince or lottery, and it updates that belief. What about self-driving cars? They're constantly using a version of this to figure out where am I on the map right now based on all the messy sensor data coming in. Even search engines, they update how relevant a page is based on how many of us click on it. It is literally everywhere, silently turning raw data into smart decisions. Look, if there is just one thing you remember from all of this, let it be this core idea. Bayesian thinking isn't about being right the first time. No one is. It's about having a system, a method for becoming a little less wrong over and over again. See, the real magic here is that Bayes' theorem isn't a one-and-done calculation. It's a loop. You start with a belief, you get some new evidence, you calculate your updated belief, your posterior. But then, and this is the cool part, today's posterior becomes tomorrow's prior. It's the new starting line. This constant cycle of updating is exactly how AI learns. It's how we learn too. And really, that's what this all boils down to. We live in a world that's just drowning in information, right? Bayes' theorem is more than just a piece of math. It's a roadmap for thinking clearly. It gives us a formal, structured way to take in new evidence and adjust what we believe, saving us from the traps and biases of our own faulty intuition. And that brings us to one final thought. Because this framework, this way of thinking, it's not just for machines. We can and probably should apply it to our own lives. So I'll leave you with this question. Think about something you really, truly believe. What belief of yours would change if you just had the right evidence?